Okay, today we discuss proof systems today and during next couple lectures, and we are going to move on to prove Gödel's incompleteness theorems. This might seem a part of logics. However, we will be heavily employing the Turing machine technology that we already proved, and also in light of recent advances in proof systems, like not proof systems, but proof checkers like Lean, writing proof checkers in Lean, Haskell and stuff. So this is becoming more and more relevant because there's a problem in scientific society, not only mathematics, that there are too many papers produced and there's too less referees to check if they're really actually true or not. So there, at some point, we should come to a computerized way to check the correctness of proofs. But that's besides the point. Let's just go back to what we are going to talk about. So the discussion starts with a question of how do we know mathematical facts? So this question probably comes from, I don't know, it is probably what ancient Greeks also asked themselves, or even before that in India or in China. But we will tackle this with a modern 20th century mathematics. With 20th century mathematics. So the question is maybe, how do we know some mathematical facts? Maybe write something like are true. Whatever this means, this is actually vague. But how do we know some mathematical facts are true? So maybe, I don't know, what should we take? So let's take something that everybody is familiar with, that the Pythagoras theorem, let's say. So if you have a right angle triangle, and this is A, this is B, this is C, then we know that C squared is A squared plus B squared. This is Pythagoras' theorem. Let's just call this thing P for Pythagoras' theorem. And so the question number one is, how do we know this is true? Does anybody have an idea? How do we know that this Pythagoras' theorem is true? I'm not asking something complicated. So how do we know? What is our notion of truth for mathematical statements, at least? Yeah, the obvious one is we prove them, right? So we prove. So we might, for the moment, even though we will address this question later, we might substitute true with provable. However, we will make this distinction, not very precisely, but we will make this distinction later. So let's say just true means provable for us. We will see that these two things are different. However, let's say provable. So P is provable, you're saying, so, right? So P is our Pythagoras' theorem. What do you mean it can be proven? That's my next question. What does it mean that P is provable? Okay, that's actually a good suggestion. So you're saying there exists some other statement, maybe let's call it, I don't know, P0, such that P0 implies P, right? This is what you're saying. Maybe there's actually a couple statements. Let's not call it P0, let's call it. So if you recall, so that there might be many different proofs of Pythagoras' theorem, but that there might be some statement, let's say usually they call them lemmas or something like, let's call them L's, just for lemmas. L1, L2, L3, and if you know L1, L2, and L3, together they imply P. This something might happen. So you use L1, so maybe L1 is something that sine squared alpha plus cosine squared alpha is 1. You know this, for example. And then maybe you use some other things also, you know, then you prove Pythagoras' theorem. And what you're saying that, okay, how do I know L1? Like, how do I know sine squared of alpha plus cosine squared of alpha is something, is true? Or how do I know L2? Then there's some other sets. So let's say, so these are all zeros, and let's say L11, L12, maybe that implies this, right? And then there's maybe other set of collection of lemmas, L21, L22, L23, and then maybe L24 that imply this. And what you very briefly said, that this chain continues, and you're saying we stop somewhere. Where do we stop? Yeah, so there, I just arbitrarily decide somewhere to stop, right? That's what, so maybe call those guys A0, A1, and A2. So let me just make some clarifications here. So a proof then is like something like a chain. But so does any of you know any axioms from geometry? Like, what will these guys be? Well, that can be taken as an axiom also. Maybe something even simpler, that if you have a line and a dot, there's only one line that is parallel to that line, or something like this. It's parallel postulate or whatever. But so my first correction is that I could have used an axiom here as well, right? Maybe for proving my P, I use some other lemmas that also require a proof that all the way go back to the axioms, but I might as well use maybe axiom 5 for proving Pythagoras directly. Right? So maybe I'm also using axiom 4 here. So what I'm saying, these L's are either provable from axioms or axioms themselves. And axioms is just an arbitrary choice of facts, according to Euclid, the things that are self-evident somehow. But whatever it is, I chose some facts, and the proof then is just a string of derivations from this fact, whatever this means, such that on every step I only use axioms or something that I already proved. Is that okay? So my next question is then, what is this? What is this arrow? So let's say now I have some sentence, let's say an axiom, and what does it mean that this axiom proves something? So let's say I have some axiom A, and I have, so for example, so I just want to tell you that you also need to specify what this is. For example, so you're doing it intuitively, of course, but what are you doing? So for example, let's say I have sentence, so there's a very famous one, let's call modus ponens. This is a logic, so you also, so you have, so what I'm going to so what I'm aiming at is that you need to specify axioms. To specify a proof, you also have to specify what are the rules that you use to go from one set of axioms or something that you proved to the next set. And modus ponens is something, the one you mentioned probably, is that let's say I proved A, and let's say I proved that if A, then B. Whatever this means, so, but somehow we have the intuitive notion what this means. So I proved A, and I proved that A implies B. Can I conclude something from this? Yes, exactly. So this is one of the rules. That means if I have two things, I have A, let's say A is an axiom, whatever, and then I also proved somehow, or there's an axiom or whatever, that A implies B, somehow this allows me to go to B. Because if A is true, and if it is true that A implies B, then B is true. Like if Socrates is a man and every man is mortal, then blah, blah, blah. this thing. This thing is called modus ponens, and this would be one of the rules. Meaning if my axiom is A and another axiom is A implies B, for example, then I would prove that B. But however, you have to specify these things. And this actually now, so we are going to be concerned with building things like this, but we're going to do it for natural numbers. So let's, instead of Pythagoras' theorem, let's think of natural numbers, and let's think of something that will be something that is not proven. So let's take Goldbach's conjecture. This conjecture says that, what does it say? Every even number is a sum of two primes. So this is what Goldbach's conjecture says, that every even number you take is a sum of two primes, and it's not proven, right? And so let me write this down. I don't know, I haven't done this before. Let's try this. That this can be written down this way. For any n which is equal to 2 times k, maybe, there exists, I don't know, p1 and there exists p2 such that n equals p1 plus p2, and I don't know, if s divides p1, then maybe s equals to 1 or s equals to p1. And the same thing with p2. So what I basically tried to write down, I don't know if it was correct with all the parentheses, is that for any number which is even, there exist two things, p1 and p2, such that this number is the sum of this p1 and p1 and p2 are prime. This is what I tried to write down, that if something divides p1, it's either 1 or p1 itself, and if something divides p2, then it is, then probably you have to also write for any s and something like this that divides. But what I'm getting at here, what is this? So let's just think that you're just a computer and you're just looking something at like this. Even though us as humans give some kind of content to the symbols, we have like this means any, and this means exists, and we have some kind of notions of any and exist and so in our heads. For a computer, this is just a string. This is just a string over the alphabet. Let's call this, so let's take the alphabet. Maybe this alphabet contains this symbol, maybe N, K, S, whatever, this P1, P2, I don't know. So this parenthesis, end, whatever, it's a finite alphabet. And it's a string over this alphabet without any meaning. So this is the distinctions between syntax and semantics. Semantics is when you give this string some kind of a meaning, that this actually means something, that for any natural number. But syntactically, this is just a string which is, so it's not just any gibberish string, right? It's not like something like this. But it's just a string over some alphabet. So this is a long way to say what I'm planning to say. So what is a proof system? Let's enlarge this. So it's a very general radical definition. Proof system S is 4 things. Sigma is an alphabet. This is the things I can write down. This any symbol, this P symbol, this equality symbol, this N symbol. So things I can write down. L is a language. Now, what is a language? Language, what I'm aiming at is things like this, some of the strings, right? I do not want all possible strings from my alphabet. I only want those strings to which I can give a meaning, whether this is true or false, maybe in the future. So language is just some of the strings. Think of them as correctly written statements somehow. For example, the statement we wrote was Goldbach's conjecture. We do not know if it's true or not, or whatever this means, but it's just a string. And so I pick some language, and I require this language to be decidable. What does decidable mean in this context? It means that when you give me a string, I should be algorithmically able to tell you whether this string is in the language or not. Meaning that, is this string well written? Does it mean anything? I should be able to say that. If I'm not able to say that, that makes no sense whatsoever. If there does not exist an algorithm that is able to tell me, okay, this language actually means, can be interpreted to mean something or whatever in the future, then it makes no sense. So I have L, which is all strings. And then in my language, now some strings represent axioms, which I just pick. So for example, for natural numbers, something like this, maybe this string, A equals B, or maybe something the reverse. Maybe this is a string, 1 plus A plus 1 equals B plus 1, implies A equals B. So this is like, this can be taken as an axiom in natural numbers, that if the successors are equal, this is one of the piano axioms, if the successors are equal, then the numbers are equal. Or you can write, there does not exist a number whose successor is 0. That would be an axiom such that 0 is the first number. So, but syntactically speaking, this is just a string. This is just some string over this alphabet, whatever this alphabet is, the same way as this is a string over this alphabet. So, by axioms, I just select some strings. If I would do it for geometry, by the way, I have to completely syntactically write down with symbols what the geometric things mean, and then with symbols, I will also write down the axioms. That will be it. And also for the axioms, I ask it to be decidable, because given a string, I should be able to tell algorithmically whether it's an axiom or not. Otherwise, if for a strings I'm not able to even say if it's an axiom or not, theoretically, then it makes no sense. So strings, just all possible, so alphabet, just some strings that are relevant strings, maybe call them this way, and some axioms. And then I also have to have decidable set of proof rules. Meaning, given two strings, how do I write down the third string? For example, we gave this example. So if you have string A, and string A equal arrow string B, maybe you have string B. But now it has, I just want to emphasize that this has completely no meaning. Even computer can do it now if you write it down this way. Computer can just manipulate strings. It just knows how to from two strings, how to produce a third one, and maybe it can produce proofs in this way. But of course, computer doesn't understand anything, what is a natural number or something like that, right? So my proof system is alphabet, language, axioms, and proof rules. The set of proof rules, this also has to be decidable, because if I'm not able to say if the rule is there or not, then it also makes no sense. Right? So in general, what is a decidable proof rule is like if you have some strings from W1 to Wi, then you have V. Somehow if you see W1 to Wi, then you can imply that V. So this is the proof system. It's very general. For any alphabet, any language, any X, any A, and any proof rules, there will be something. Of course, most of them can make no sense whatsoever, but whatever. So what is a proof then? Let's look. It's exactly what you said. A proof is a sequence of strings, W0 up to WT. So this hashtag just separates them. We always think of hashtag as not being in a letter, so it's like a meta thing. So it never occurs in W1 or W2, so you can exactly tell where the hashtag occurs, that okay, W1 is finished, W0 is finished. So a proof is a sequence, again, it's just a long string with the hashtags W1 to W2, such that each Wi is an axiom, or any next one is a derivation of the previous ones. That's it. So this is exactly what you said. So this thing will be a proof of WT, let's say. What is a proof of statement WT? Every previous one is either an axiom, because then I kind of think of axioms as being true, whatever this means, or every previous one can be gotten from the derivation rule from the ones before that. Okay, for example, what is W0? By these two rules here, it forces W0 to be what? Yeah, because there's nothing before W0, so it cannot be derived. So what this says that Wi is J1 to Jn, it's less than Wi, so Wji1 to Wjn is the things that sit before it. So W0, there's nothing before it, so you cannot use this rule, so it has to be an axiom. Now W1, so W0 is an axiom. W1 either is also an axiom or can be derived from W0 from one of the rules that you specified. Then W2 is either an axiom itself or can be derived from W0 or W1 using derivation rules. Okay, this is exactly what we specified where? Did I turn this off? Turn it off? I guess so. So this means that we will write that in proof system S, I can prove WT. That means such a string exists. Okay. So now it comes lemma number 1, and you should tell me why this is true. What does lemma 1 say? Lemma 1 says the set of proofs in any proof system. So what is the set of proofs? These are all strings that are proofs, meaning they obey the rule that every string is derived from the strings before it or is an axiom. Every proof in S is decidable. Let's address this one first. What does it mean? It means that I can algorithmically, if I give you a long string, you can tell me algorithmically whether this is a proof or not. So let's say I give you a string, how would you check whether it's a proof or not? So you should be able to tell me yes or no. Exactly. How? So so you start here. For W0, you check whether if it's an axiom. Why can you say yes or no? Finite array. Decidable array. Just because axioms are decidable, you can check whether W0 is an axiom or not. Axioms are not finite. One of the axioms is, for example, the axiom of induction. Right? In natural numbers, induktia shegulia gamoviveno. That is actually infinitely many things. But okay, we'll get back to that. Is it though? Okay, let's see. Maybe not. Okay, so, but W0, you can check whether it's an axiom or not. What about W1? How do you check on W1? Yeah, exactly. You check it's an axiom or not, and then you have to check whether it is implied from W0 using the rules, and the rules are also decidable, so you can check all the rules and check whether there is a rule from W0, and you just go on doing like this, and in the end you finish. So you basically use syntactic, so computer can syntactically check whether proof is valid if it's written in this form. So think about what we're saying. You're saying that if you give computer a proof, it will tell you this proof is valid or not. Any proof. Now, let's look at the different thing. Let's look at set of provable strings. This is completely different. What is a set of provable strings? These are all strings for which the proof exists. What would this mean? Let's say, is it decidable? Well, in general, what is your intuition? I mean, you cannot answer, but so if this were decidable, look what it means. It means that I will give you a string and you can algorithmically tell me whether it is provable or not. For example, I erase this. If I give you a string that corresponds to Goldbach conjecture, your algorithm should be able to tell me, oh, it's provable or not. Yeah, so it makes kind of intuitively this thing replaces a mathematician. If there's something that decides this, it's like you give it a string which represents a theorem and tells you, yes, it's provable, no, it's not provable. If this were possible, somehow this would be heaven, or maybe hell, I don't know. But in general, maybe for some proof systems which are very, because you kind of have to specify a proof system, right? Maybe it just has one letter and one axiom, whatever, then it's possible. But in general, this is, our intuition tells you that this cannot be decidable. However, it's recursively enumerable, meaning it has an acceptor. How? Acceptor meaning if the string is provable, eventually you can find the proof. How? You just go over all possible combinations. So you enumerate all possible strings. So you take your hashtag, you take all possible letters you can write down. This is finite, right? You take all possible strings, all possible combinations. You enumerate them by length and then by lexicographically. And for each string, you test if it's a proof or not, because you can do that. And you will enumerate all provable strings. You test. So you look at all possible strings, test first one, test second one, test third. Okay, this is a proof. But if something is not provable, you have no way of knowing that it's not provable somehow. You're waiting, and you're just waiting for all proofs to appear, and maybe your thing never appears. So set of provable strings is very different than set of proofs, which is decidable. This is undecidable on the, well, it's what we proved here, it's recursively enumerable. We said nothing about decidability, but somehow our intuition tells us that this is not so easy. Huh? Okay, so this is very general. If you give it one more thought, if you think about it 2 more minutes, you will see that it is extremely general. This is just general alphabet, general language, whatever you pick. But of course, humans do not do this. They pick specific axioms motivated by the real world around them, and they pick specific symbols and specific derivation things. And so we are going to try to build the important proof system of elementary number theory. So elementary number theory is addition and multiplication on natural numbers. So let's start to build this. So we call this proof system ZE, for I guess for Zeile or something German. E for elementary. So this will be letters I can use, the language, the correctly written things for natural numbers, axioms of natural numbers, usually known as Peano axioms, and the rules that I'm using. We're not gonna, even though we try, we're not gonna be very detailed, and we're gonna skim over some things because otherwise this goes very deep. So first and the easiest one is the syntax, meaning not syntax, but what are the letters that I want to use. So what are the symbols I want to use? I want to use 0, I want to use 1. I want to be able to write down 0 and 1. They have no meaning. These are just symbols. I want to be able to write down V and C. So remember in Goldbach's conjecture, I wrote P1, P2, S, L, M. Instead, I will write V's and C's. V will be used for variables and C's will be used for constants. And I will not, instead of writing V, let's say, what I'm aiming at is that instead of writing, maybe, where is my pen? So instead of writing maybe V2, I want to be able to write something, second variable. Like instead of P's, I always write V's. I will write something like this. Okay, so I will think of 0 and 1 as binary numbers, and 10 will be 2, and instead of writing this down here, I write this way. So 0, 1, and V just allows me to write anything I like. I just write 15 in binary and it will be whatever this thing is. Okay? This is what I am using this for. So 0 and 1 actually give me all natural numbers. It's just a pure string. It means nothing, but in my head. V will be for variables and C will be for constants. We will make this distinction in a minute. Then I want parentheses. I want plus multiplication equals and or, even though I say and or, these are just symbols. And conjunction, disjunction, and this will be used for not. So to say not something. This is implies, exists, and any. This is it. This is my alphabet. It's finite. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 symbols. This is all I need to write down all mathematical statements for natural numbers. Come on, next. Okay. So now I give you a definition. So the ones that I already told you about. So V I will call set of variables. This is just V and a string. The string is zeros and ones. So basically it's V001, V10. So I think of it as V2. So these are just the symbol V and then the double. So V consists of strings over this alphabet. So it's like a language over this alphabet of variables. And the same way I define constants. Constants are again C and then string in 0 and 1s, but also 0 and 1, I call them constants. The constants are 0, 1 and C1, C10, C110 and things like this. You will see in a minute what I want. Let's skip this for a moment and we'll come back to this. Yes, let's come back to this. And now I will define terms. What are terms? This is the very important definition. A term, what is a term? What I'm aiming is to write down the correctly written down things in natural numbers. So I want something like this to be a term, like you see here. I want something like V10 plus 1 times C11 to be a term with correctly written parentheses, but parenthesis plus should not be a term. So I want to single out those strings that I can attribute a meaning as some kind of something written down in natural numbers, subconstants and variables. So for example, what would be a term? What is the definition of terms purely syntactically? Constants are terms, variables are terms. Now, if A and B is a term, then also A plus B parenthesis is a term and A times B parenthesis is a term. That's it. Okay, this allows me to write down things like this because why? This is a term because this is a constant, this is a variable, right? Then this plus this parenthesis is a term, then this is now a term, this times this is also a term as a constant, parenthesis is a term. So if you do this, you will kind of get all possible expressions, this is the word that I'm looking for, all possible expressions in variables and numbers like this, 1 and things like this. Okay. And now we move on to another very important definition. These two are the main players here. What is a predicate? So let me give you what is an arithmetic predicate. Now arithmetic predicate is again a string over in this whatever I have not specified the language yet, but whatever language I'm building, it's a string, but somehow the term was some kind of expression in natural numbers, right? Like A plus B. But the arithmetic predicate would be something that I'm thinking of having a truth value. Is A plus B true? I mean, it has no meaning. But A equals B is somehow either true or not in my head. So by arithmetic predicates, I build strings that will have some kind of a truth meaning attached to it. What is predicate? Syntactically, this is, if you have terms A and B, think of expressions, so in natural numbers of A and B, then A equals B with parentheses is a predicate. So for example, V10 plus 1 equals V11 plus C11 is a predicate. Now, if A and B are predicates, then not A is a predicate, A and B is a predicate, A or B is a predicate, and A implies B is a predicate. So if I have A equals B or A plus 1 equals B minus V0, this is a predicate, right? And very importantly here is that if Y is a variable and A is a predicate, the followings are predicates. There exists Y such that A, and for any Y, A. Okay, so if you have some predicate V10 plus 1 equals V11, then for any V10, V10 plus 1 equals V11 would be a predicate. So for example, and that's it. For example, something like this would be a predicate. For any V0 and for any V1, V0 plus V1 equals V1 plus V0 plus V10 is a predicate. And you see that there are many parentheses here, but you can completely get rid of them. How do you get rid of them? You just pick the priorities. That first you do multiplication, then you do addition, then you do equality from school, then you do this, then this, then this, then this, then this, and then this. So then you do not have to write parentheses every single time, right? Okay, now we have to talk about the thing that I skipped. What is the main difference between, how much time do I have? Still have time. What is the difference between bound and free variables? Okay, let me explain the intuition for you first. Let's go back to whatever this thing is. Where was this? If you think of it, if you look at this thing here, and let's say it has some kind of, by the way, this one has to be a bigger one here. This makes no sense because we do not have, so it's V1, like this. This and this should be the same. So let's think of let's say this represents some natural numbers, V0, V1, and let's say this has a truth value, even though it doesn't at the moment. What does the truth value of this depend on? On which variable does the truth value of this statement depend on? Okay, let me tell you what if V10 is 3? Is this statement true? Okay, let's pause this and ponder. So let's say I erase this here. Let's say it's written this way. Then what does the value of, on what value does what value of the variable does this thing depend on? So yeah, this is an example. Yeah, because but somehow what I'm claiming, maybe I should give you another. Let's look at here. Let's look here, this place here, and let's rewrite them without binary. So this says V2 plus 1 times C11. Let's erase the C. Let's look at this predicate here. Maybe make it 3. Is this true or not? If you're intuitively. It depends what V2 is, right? Sometimes it's true, somehow. It depends on V2. If V2 is 2, then it's true. But now if I make something like this, is this true? No, right? Because for any v2, v2 plus 1 is not 3. So what I did by doing this, I bounded this variable. So intuitively speaking, I'm going to purely syntactically write it down, what it means to have a bound and free variable. Here, in this expression here, v2 was a free variable. Somehow you can think of that this thing depends on v2 somehow. But in this case, when I put this any here, v2 became a bound variable. So the truth falseness in our head, whatever this means, somehow now does not depend on v2 anymore. It's bound. The same thing is this true now? So you told me this is false for natural numbers, but what about this one? This is always true. Again, before I had this expression that had no particular truth value because it had a free variable v2, but as soon as I bounded this variable, this kind of collapsed into true or false bin somehow. This is the difference between free and bound variables. Even though I raised it, remember our string in Goldbach conjecture that we wrote down? Did it have free variables? Can you think of it? No, think of it logically somehow. If it would have free variables, doesn't that mean that the whole statement, the truth of the whole statement, depends on the value of the variable? So it cannot have a free variable. Somehow, the statements that you're trying to make, all variables should be bound. The bound variables, the things that are bound by, they call it the quantifiers like this, are actually dummy variables. They do not represent anything. So if you think of it this way, I even can go beyond the natural numbers and think of a function fx equals x squared. This is a bound variable here. This x this function does not really depend on x at all. This is a function that assigns 3 to 9 and 4 to 16. It doesn't have to do it. If I change even the name of the variable y equals y squared, the function stays the same. So this is like a dummy variable. The same thing you have seen when in a summation symbol you have I goes from 1 to whatever. Doesn't really matter what I is a dummy variable there, right? The same thing happens here. So this is the difference between free and bound variables. So you can intuitively think that if I have a free variable in there, then this free variable, the value of the statement depends on the value of the variable. Then it's free. And I also want to probably mention and go back here at some point because otherwise we're confusing everything. So for variables, we have free and bound by quantifiers, this statement that I said. And what are constants now? What are constants is, it's exactly, they serve as intermediate variables in proofs. You might be able to construct some mathematics when there's actually, I think Bourbakis do that. So there is no difference between constants and variables, but let's actually make them. So the good example to understand, so what is a constant and what is a variable, if C and C prime, if for constants you prove that C plus C prime equals C prime plus C, you should be able to infer that for any x, the variable x, and variable x prime, x plus x prime equals x prime plus x. So think of it this way. When you prove that I took some constant c and I took some constant c prime, and c plus c prime equals c prime plus c, I proved this. That means that for any x and any x prime, x plus x prime is x prime plus x. Or, for example, if you prove something like this, there exists V such that AV holds, A is some expression, let's say, and you just AV is when you plug in V into this expression. This actually means that AC holds for some constant C. I try to give you throw at you some examples so that you understand what is the difference between variables and constants. Variables serve as something that run around and change values. However, constants, even though in the name they're still look like variables, you're supposed to think of them as fixed things. But again, proving something like this for general two constants implies something like this. But okay, so we will get back to this even more, and we have 2 more minutes, and maybe give you a definition, just purely syntactically, a computer definition of what it means to have free and bound variables. So purely syntactically, without any content, without any semantics. So if y is a variable, and let's say a and b are terms, meaning it's like some kind of, think of it as an expression in natural numbers, and y occurs in a or b, then y occurs free in a equals b. So you have some expression in natural numbers that contains a variable, and it has another expression in natural numbers, let's say, then, so this is obvious, right? So if you think of it, let's say you have an expression 1 plus v equals 3. Well, 1 plus v, and the other expression you have 3 plus 2. By the way, I'm writing 1s, 3s, and 2s, but I have not allowed myself to, I just realized, I only allowed 0 and 1, but I will be able to do this because I can write 3 as 1 plus 1 plus 1. But for now, let's say I can write this, and let's say this is a term, then in here, the value of this statement depends on v, so it's free in here. This is what it says. Okay, let me just go through this and we're finished. So if a and b are terms and y occurs in a or b, then this occurs this way. Then the most important one is that if you have a predicate and y occurs in a, then y occurs bound in there exists ya, and what happened? There exists ya, and for any ya, this is what I described to you by bounding the variable by these quantifiers. And then the third rule is that if you have a predicate, then the free and bound occurrences of y do not change in. By the way, I keep saying this, so let me just make this caveat that there's a free variable and bound variable. I should have also always said the occurrence of y is free or bound. Not the variable itself. Is the same variable can occur free somewhere and bound somewhere. So the free and boundness is the property of not the variable but the occurrence of the variable. It either occurs free or it occurs bound. And this one, number 3, says that if it's the occurrence, the free and bound occurrences of variables do not change in the sentences a and b, a or b, and a implies b. So these are the free and bound occurrences here are free and bound occurrences of y in a and free and bound occurrences of y in b. And finishing off, a statement is a predicate without free variables. For example, the Goldbach's conjecture that we wrote down was a statement because the truth value of it in our heads does not depend on the variable. So a statement is any predicate, something that has a truth value in our heads, such that its truth value is somehow fixed. It does not have free variables. For example, what is a statement? What is not a statement? C plus C prime equals C prime plus C is a statement because it only contains constants, and you should think of them as C plus C prime equals C prime plus C is just a constant. It has a truth value. Oh, it's actually a good example to see a difference between constants and variables. Here, C plus C prime equals C prime plus C has a truth value in your head. However, if this were variable, it has no truth value because variable is running around and changing. And V plus V1 is not a statement. And this finishing, the language of elementary number theory is all statements. So all strings, such that all variables there are bound. So they're, well, or they do not occur. So a language is all statements such that they are predicates, that means they have 0, 1 value in our heads, and they are without free variables. So something that is a candidate to be proven or disproven, basically that's what it is. Otherwise, okay, let's pause it and you can ask questions.